Assalamu alaikum, dear students. I'm very thrilled to be back with you with another video lesson. We're continuing with all the lessons, and of course we've covered chapter 1, chapter 2, chapter 3, and chapter 4. Today we'll begin with chapter 5. Chapter 5 is a bit different than the chapters that we've studied because it is about magnetism basically. And of course it is something that perhaps you've dealt with magnets, or perhaps you had some magnets, let's say, and of course just to play for fun, let's say. Okay, so what are we going to cover in this unit? We're going to, that is basically magnetism. We're going to cover magnetic fields. These are basically the chapter preview. Basically, that is what we're going to go through. And of course, we're going to talk about magnetic field and magnetic flux. Basically, when we say the magnetic field, basically the field around a magnet, as you can see here. And then after that, we're going to cover magnetism from electricity. So how are we going to create, to induce, to generate, or just induce, let's say, or create would be the more proper word in this case, let's say to create or induce a magnetic field around a wire, let's say. And of course, who was the scientist behind this, let's say, or the one who discovered. And then after that, of course, we're going to talk about magnetic field of a loop, you can say. And then after that, we are going to talk about a magnetic force here. And of course, we did talk about a lot of force. We talked about tension, we talked about friction, let's say. We talked about, let's say, gravitational force, yeah? And another force that we have is basically magnetic force. So generally, what happens, let's say, to a charged particle, whether a proton or an electron, when it goes into a magnetic field, or let's say if a wire is let's say carrying current, if it is inside a magnetic field, what will happen to that wire, let's say? Or if we have two wires that are carrying current, of course, like what will happen to the two wires, yeah? Okay, and of course there is a force, let's say on these or between these, that we're going to cover later on, inshallah. Okay, so let's begin with the first section, which is basically section 5.1, and that is magnetic field. In order to understand or to learn about magnetic field, first we need to know what are magnets in general. So we can say magnets are, like, let's say, materials that can attract magnetic materials. Remember, magnet can attract magnetic material. What is the difference between the two? Magnet is the, let's say, the thing. Magnetic material are those things that will be attracted by the magnet. Remember this. But let me ask you a question. Can a magnetic material ever be repelled by a magnet? I'll leave the answer to you, so you think about this one here. Now, this is basically a bar magnet, or the shape of a bar magnet. Yeah, we have different types of magnet. It could be, let's say, a bar magnet, horseshoe magnet, it could be a ring magnet, whatever, yeah? Different types or sort of magnets here. Every single magnet, no matter how big or small, it has two poles. And of course, these are North Pole and South Pole. Very good. And then we do know that like poles repel one another. And if it is unlike poles, they will attract one another. So let's take a look at this one here. Okay, so remember this. Let's get this one back to the side. I think we can't. Okay, so going through this one, take a look. Remember, we have a magnet. Let's say this is basically a magnet. We have North Pole and South Pole of a magnet. Okay, and of course, let's say we do know that if I cut this magnet into two pieces, okay, what do you think will happen if I cut this one into two pieces? Remember this. You might say one side would be north, the other side would be south. No. No matter how many times you cut it into two pieces, always one side becomes north and the other side becomes south. Even if you cut, let's say, this part of a magnet, it doesn't matter how tiny, how small it is, whenever you break something into, let's say, or a magnet into two, of course, always one side becomes north and the other side becomes south. Remember this. That is basically the nature of a magnet. We can never ever have a magnet with one pole. Remember this. Okay, now let's talk about then the second thing, like how do magnets attract or repel one another? Let's say if we have magnets, let's say, these are basically bar magnets, okay? Let's take three cases, okay? So these are, let's say, North Pole and South Pole, North Pole and South Pole, and then South and South, North and North, let's say, and of course we have North and South, let's say, and then North and South. Take a look here. Now these two magnets, of course, their North Pole are closer. So what happens when I bring them closer? If I bring them closer, of course, these two magnets will repel one another, guys, okay? So if I bring these two magnets closer, because north and north, so they repel one another. So these two magnets will move away, push away one another. What if we flip the magnets like south and south? They will also repel one another, okay? Should have drawn the arrows below, but that makes no difference here. But what if it is, for example, flip one of the magnets, we have north and south. In this case, of course, they are going to attract one another. So based on this, we can say like poles repel. Like poles repel, but if it is unlike poles, they can attract one another. Okay, another thing that we have is basically it is a compass. What is a compass? Basically, you've learned about a compass, let's say, is basically it has a magnetic needle, you can say, or you can say compass is basically another type of a magnet. It is like a needle or magnetic needle, but this magnetic needle, of course, it can swing freely on a pivot. Why? So that it can shows you the direction, for example, yeah? And of course, let's say this is basically a compass, yeah? A compass normally shows you the direction, yeah? So what is a compass? You can say it is a magnetic needle that swings freely on a pivot. But how do compasses align themselves or, let's say, show the direction? These compasses normally align themselves with the direction of what? With the direction of the Earth's magnetic field line. And of course, let's say if this is the Earth here, okay, we have North Pole and South Pole, yeah? And of course, we have magnetic fields, let's say, around the Earth as well, yeah? So now the magnetic field around the Earth, I should have used a different color though. So let's say these are the magnetic fields here. The magnetic fields of the Earth, let's say. So these are the directions of the Earth's magnetic field. So if we add a compass here, yeah, that's what that one too. So if we add a compass to this, if we add a compass, let's say here, you would see that the compass would align itself just so that, you know, like align itself with the Earth's magnetic field line here. So if you have another compass here, it would align itself just like this one so that it shows you north and this. What happens if you put a compass here? And of course it will align itself so that it can point north in here. That is basically a compass, and sometimes you can see the arrow of a compass, and some other times you might see something like this. And the top part is basically colored red. That means it points or indicates the pointer or the arrow of a compass here. So basically that is a compass. But remember this, a compass can show you the direction north and south only if this compass is not interfered with any other magnetic field. What does it mean? That means this compass will show you the direction correctly as long as there is no other magnets close to this or any other magnetic field, because it could be a magnet, it could be a wire that is carrying current here. So this compass shows you the direction correctly as long as there is no other magnetic fields close to this compass here. Okay, so these are basically when we have magnets, you can see, like unlike poles attract one another, and if it is like poles, they will repel one another. And this is basically the direction of the magnetic field, which is we're going to talk about this in a second. Now, magnetism and magnetic materials. Now, ask yourself a question, can magnets attract every other material? The answer is no. So what are those materials that a magnet can attract them? And of course, these materials are only those that are containing iron, yeah? So we can say magnets can attract iron-containing material. So any material that can contain iron, of course, magnets can attract them. And by the way, magnets can be varied in different sizes and shapes, yeah? So if you see a magnet like this, for example, or something smaller, it doesn't mean that the smaller magnet is weaker, no. That is basically depends on many factors. So the strength of the magnet, it doesn't depend on the shape, yeah? We have small magnets but are very strong, and of course we can have large magnets that are less strong, let's say. And this is basically a compass, shows you, or you can say this compass, when it is not close to any other magnetic fields, it can show you the direction of the Earth's, let's say, geographic poles normally. Why? Because it can align itself with the Earth's magnetic field line here. Okay, now let's talk about magnetic field and magnetic flux. Let's talk about magnetic field, yes? What is a magnetic field, guys? So we can say magnetic field is normally, all right, let's see. Magnetic field is normally, it is a region. So let's say we have a magnetic or a bar magnet, And of course, this is north and this is south, let's say. Okay, so watch this. If I add a paper clip here, okay, if I have a paper clip, this paper clip will be clearly attracted to the magnet. What if I add another paper clip here? Okay, by the way, it could be a screw, it could be a nail, it doesn't matter. As long as any material that contains iron, it can be attracted to this magnet. And of course, you can add another, let's say, metal or iron here. Iron, not metal, because not all metals can be attracted to this. Okay, so it can still be attracted to the magnet, yes? So we can say there is a region around a magnet where these objects can be attracted. What if I put or add another paper clip right here? Do you think this magnet will be able to attract this iron nail? The answer is no. So here's how we can define a magnetic field, yes? Remember, a magnetic field, that is a region around a magnet where magnetic force can be detected. I'll repeat the definition. Magnetic field, B, all right, magnetic field, and by the way, it is a vector quantity as well, you can say. So it has both magnitude and direction here. So magnetic field, it is a region around, it's like, you see field, for example, it's like a fence around something. That is basically anything inside the fence, that is inside the field, you can say. If it is something out of the fence, that is out of the field here. So we can use the same analogy for magnetic field, or not only magnetic field, we had gravitational field as well back in the previous lessons, yeah? So magnetic field, you can say it is a region around the magnet where magnetic force can be detected. What do you mean by magnetic force can be detected? That means if you add, or if you, for example, leave an iron containing object here, it would be attracted. So of course there is a force can pull this nail, this, let's say, paper clip towards the magnet. That is what we mean by magnetic force can be detected. If not, let's say, if you add a compass or bring a compass here, and of course this compass would, you can see that later on, it will point to one of the directions, let's say, okay? Or this compass, let's say, it would deflect because of this magnet, no longer shows you the direction north-south of the Earth, yeah? Okay, so this is basically magnetic field. Now, let me emphasize on this a little bit, like before going to this, I should have done this one here. So if this is a magnetic field, we can say, we can draw the magnetic field lines, yeah? So if this is the bar magnet, once again, north and south, we can say magnetic field lines are something like this, okay? How about if I use a different color? So magnetic field, let's use this. These are basically magnetic field around the needle. And of course you can see here, and by the way, these magnetic field lines, you can see they form closed loops here. We'll talk about this in a second. But the magnetic field lines normally go from north to south. So we can say the direction, by the way, these lines represent the direction of the magnetic field, yeah? Okay, so the direction of the magnetic field, it is always from north to south, but that is out of the magnetic field, let's say, or out of the magnetic bar. These fields, remember, they form closed loops here. So if I drew something like this, that is a closed loop, yes? If I take only this part, inside the magnet, you can see that if this is the direction, so what is the direction of the magnetic field inside the magnet? It is going to be from south to what? South to north, you can say. So the direction of the magnetic field, it is outside the magnet. It is always from north to south, from north to south. But inside the magnet here, if I draw it here, because these field lines form a closed loop here, so it has to go like this, then here's the direction, then continue, yeah? Or if that is the case here, it goes like this and then comes back here. So this is a closed loop of a magnetic field here. And by the way, the closer the lines to one another, that means the stronger the field, yeah? And of course, if these lines are far from one another, that means the magnetic field is less strong here. So you can see here, if I compare two regions, let's say, or 2 points here, okay, let's say now we have a material, or there is an object at point A here, and then there is another object at point B here. I think the drawing is a bit messy. Let me clear this up and redraw this one more time, yes? So here we have a bar magnet, north and south, yes? I'll draw perhaps one line here, or maybe I'll make it 2. Should have used a different color though. Okay, let's make it more interesting. Okay, so is it jammed? No, still working. Okay, I think it is not. Okay, so let's see. Yes. So this is basically the magnetic field around a magnet. We don't draw too much, okay? That is this. So if I have, let's say, or if I put, oh, that's over there. Okay. All right. So if I have an object at this point, let's say at point A, and then another object at point B here, which one of these objects would experience a greater force? And of course it is, let's say, point or object B. The reason why, because you can see that the magnetic field lines of this region are closer to one another. So if magnetic field lines are closer, it means that the magnetic force will be stronger here. The closer the lines, you can say, the stronger the magnetic field. The stronger the magnetic field will lead to a stronger magnetic force. So we can see that this object, of course, would experience a bigger magnetic force compared to this one here. Now, how can we tell, or how do we know the magnetic field lines look like this? How do you know that I didn't draw this on my own, let's say? Well, here is a way to find this, yeah? Now, there are two ways to find or to see, let's say, the magnetic field around a wire, around a magnet. And how do we do that? Or how do we know this? Yes. One way to know this, let's say, if I have a magnet, or piece of magnet, let's say this is north and this is south. And of course, we can use iron filings. So what are iron filings? You can say small pieces of iron, yes? And of course, so that we can have the correct shape here, it would be best if you use the magnet under a paper, a thin paper, so that these iron filings, they don't stick, let's say, to the magnet, because once they stick to the magnet, because they are very small, tiny, it would be very hard to, let's say, or detach it, let's say. So if that is the case, how about if I cover this, let's say, magnet with this? So in this case, imagine this is basically the shape. The magnet is below the paper. I'm going to move this one or redraw this one here. And then the magnet, here's a magnet below the paper, and here's the paper. So what happens when we spray iron filings onto the paper here? So of course, let's say this is the paper, so that in order to avoid mixing with the drawing here, so I'll just erase this tree here. So imagine this is the front of the paper, and this magnet is below this. So what do you see or observe once you do this? Let's use this. So of course you would see that these iron filings here, of course, would align themselves, let's say, around the magnet here. So you can see that if this is the magnet here, okay, you would see that a lot of iron filings would be like this, and of course you would see that shapes like this here. Let's make it more obvious, and of course you would see something like this, yeah? So you would see basically lines of iron filings, or iron filings would be aligning themselves in like these forms here. And of course you would see that a lot of iron filings will be connected to these, because we said that magnetic field is stronger at the poles, at the end. You can say at the poles, not at the edges, at the poles. So this is what you observe on a paper, but isn't this the same as these, right? So we can use iron filings to determine, to see the shape of the magnetic field. Yes, that is one. There is another way to see the shape of a magnetic field. What is the second way? The second way is by using a compass here. So if I have a magnet here, let's say this is north and south. Okay, so if I have, or let's say if I add some compasses, let's use a different color here. So let's say these are different compasses here. And of course at different locations, we can have a compass here as well. So remember this, normally compasses show the direction north and south. But once you bring them close to a magnet, of course now they no longer show north and south. They would align themselves with the, or you can say with the magnetic field lines of this field, okay? Or the field lines of this magnet, you can say. Okay, so moving on with this, let's say, so if that is the case, remember the compass would point in this direction, yeah? For this compass here, you can see that it would point in this direction. For this one, it would point in this direction. For this one here, it would point in, my bad, I think it did the opposite. Okay, so it's supposed to go the other way around. Okay, so watch out. So remember, if that is a compass, this is north of a compass, and this is south of a compass. So north and north repel, of course. South and south repel, but north and south, they attract. So if that is the case, if I add this one here, so of course the compass is going to be, I think I was drawing it correctly, or maybe not. Okay, so this one is going to be, remember, this is north of a compass and this is south, so they attract. What about at the other side? Because remember this, it has to point away because this is south, south, and north attract. What about this one here is going to be like this. If not, you can draw a little bit straighter here. So we can say something like this. And then if it is at a point here, of course, it's going to be like this. So if you have or align a lot of compasses here, see that this one would also point this. Okay, so now I can draw the magnetic field lines, yes? So based on this, I can say the magnetic field lines must look like this one here. And of course, by using a lot of compasses, you would exactly get magnetic field lines here. Okay, let's erase this one here. So if that is a magnet, north and south, then you would see that the magnetic field lines would look like this. But let me ask you a question. How do we know which way the direction is of the magnetic field lines? We said there are two ways to see that the magnetic field lines around a magnet, using iron fouling and using a compass. But what can we use to find the direction of the magnetic field? Like, which one of these can be used to tell which direction is the magnetic field? That is only a compass, guys. So do not fall into this, yeah? If they ever tell you, for example, what can we use to see the direction of the magnetic field line? By the way, these are imaginary lines. We don't see the lines, yeah? But we can see the effect of these lines. For example, they can make a compass needle to shift this way. That means this is the direction. So once again, we can see the direction of the magnetic field line by using what? By using a compass only, guys. So remember this. How can we see which way it is, for example, let's say, which side is north and south? That is only by using a compass. We can only use a compass to find the direction of the magnetic field lines. But if you just want to see the magnetic field, then of course you can use either iron filings or compass. But for the direction, you can only use, like to see which direction is the magnetic field, you can only use a compass here. Okay. So once again, so how can we, redefining the magnetic field? We said it is a region in which a magnetic force can be detected. I forgot to mention the unit of a magnetic field. Okay, the unit of a magnetic field strength is basically, it is measured in Tesla. Okay, the unit for magnetic field is basically measured in Tesla. Okay, now the magnetic field B is a vector quantity. That means it has both magnitude and direction, which you already know what are vectors, yes? Now, drawing the lines of a magnetic field, how can we tell, once again, how can we tell the direction of a magnetic field? Remember, if you want to know the direction, you have to use a compass. But if you just want to, let's say, see the effect, or let's say you just want to see the magnetic field lines, then of course you can use the iron fouling. So there's a difference between the two. You want to see the direction, you have to use a compass. Or you just want to see the magnetic field line, you can use both iron foulings and a compass. So how we can do that? Take a look. This is basically the magnetic field lines around a bar magnet. Okay, if you add some compasses here, you can see that these are basically, the red side basically, or represents the tip of an arrow. Basically, each one of these are pointing to the south. So the compass would align itself with the bar magnet's magnetic field line, you can say. And watch this. You can see, this is a more obvious example you can see, okay? So these iron foulings, you can tell you the direction of the, not the direction, just the magnetic field around a magnet, yeah? But if you want to see which direction it is, then of course you'll have to use a compass so that you can tell, like, which direction is the magnetic field lines are going. By the way, there are more tips about this one. These magnetic field lines, they don't have any beginning or end, yeah? All right, so as long as there is a magnet there, these loops are closed loops, so no beginning or no end for this. Take a look at this question. It says, how can the direction of the magnetic field line be determined? The direction. For the direction, you have to use a compass. What is a compass? It is a freely rotating magnetic needle, you can say. Does that mean I can use any other magnet if I can allow them spin freely? The answer is yes. Imagine if this is a magnet. If I use a string here and suspend it in the air so that this magnet can spin freely, let's say I want to use it as a compass. I can do that, by the way, okay? If this is a magnet, attach string to the magnet and let it spin freely. later on, once it stops swinging, you will see that one side will point north and then the other side points south. So the north points north and the south points south. What if it is close to another magnet? Then of course these two ends would align itself with the magnetic field line of that magnet. Don't forget. Okay, so if a small freely suspended bar magnet, such as a needle of a compass, is brought near the magnetic field, the compass needle will align itself with the magnet's, you can say, or magnetic field line. That's one. But remember this, guys, this note. Iron filings can be used to show the magnetic field, but not the direction. So you can see, we can see the magnetic field, but not the direction. If you want to see the direction, you have to use a compass. I've emphasized, I believe I've repeated this so many times so that you know the difference between the two. These points are also very important. Remember, the direction of the magnetic field be at any location. How do we find the direction of the magnetic field, guys? Remember, we'll say the direction of the magnetic field at any location is basically the direction where it points north, you can say, or where a compass points north. So let's say, what is the direction of the magnetic field for this line? Okay, the direction of the magnetic, if we have a compass here, you would see that the compass will point in this direction. That means the magnetic field is basically pointing this direction here. Okay, so the direction of the magnetic field line B, okay, at any point is basically the direction where a compass points, or a compass points. Okay. Now, the other point that we have at that point, of course, or that location, magnetic field lines appear to begin at North Pole, and of course, appears to begin at the North Pole of a magnet and end to the South Pole of a magnet. These are basically, they appear. Otherwise, there is no beginning or end for this. They just form a closed loop in here. Okay. Magnetic field lines have no beginning or end. Rather, they always form a closed loop here. So the closer the lines, the stronger the magnetic field, which we've also said that as well. Now, convection of representing the direction of a magnetic field, guys. Of course, we have different sets of direction, but for now, we only go through this three for now. Okay, so you've seen an arrow. Okay, if not, at least on TV, let's say. Okay, so imagine this board or the screen is basically the plane of a page, yeah? Or maybe if I have another page, let's say, we can say, if that is the case, for example, if the magnetic field line, or if the direction, let's say it is upward here, we can say, you know, like let's say towards the top of the page, yeah? What if it is downward? We can say towards the bottom of the page. As a matter of fact, let me use something different. Let's erase this, yeah? So here, let's say we have a page, yeah? Consider this part, or this red rectangle as a page, yeah? So if I go upward, basically, that is towards the top of the page, yeah? This is top, this is bottom, okay? And of course, you can say this is right, or towards the right, and this is left, yeah? And of course, what if it is into the page? And of course, we can have out of the page as well. So imagine if this is a pen, the tip of the pen, and of course, this is the back of the pen. If I go this way, that is into the page, yeah? If I go the other way, that is out of the page. Now we get to this one into a second. So that is towards the top of the page, this is towards the bottom of the page, and this is, of course, to the right of the page, and this is to the left of the page, you can say. What if it is into or out of the page here? If it is into the page, let's use this color. If it is into the page, now consider this arrow here, yeah? If it is moving into the page, which part of the arrow you would see that? You'll see the end of the area. So if it is into the page, of course, we'll use a cross, okay? Assuming that you only see the bottom or not the end of the arrow. That is, if it is going into the page, just like this one here. But if it is coming out of the page, you would see the tip of the arrow here, which is coming towards you. So you only see this tip, and this is basically how it is represented. So if it is a cross, so we can say this, going back to this. Let's go back a few steps. Maybe this one is easier. So if it is into the page, guys, this is what you're going to see. Into the page, you would see the end of the arrow, and that is what you see. But if it is out of the page, of course, you're going to see the tip of the page, which is coming towards you here. Okay, and this is going away from you. These are, of course, later on we'll emphasize on this a little bit more, because we could have different sets of directions. Yeah, we could go with x, y axis, z. Let's say we could go north, south, or whatever, or we could use the page as a direction there. Okay. So that is basically, these are for now. Later on, of course, we'll go something else, which is magnetic flux. What is magnetic flux? Of course, we did talk about magnetic field, yeah? So what is magnetic field? You can say a region where magnetic force can be detected, yes? So magnetic field is a vector quantity, so it has both direction and magnitude. For the direction, we said the magnetic field is always going from north to south. And how we can tell, or how can we see, we don't see the magnetic field line, but how can we see the effect of that? By using a compass. What about using an iron filings, let's say? You can see the magnetic field lines, but not the direction, okay? Now here we have magnetic flux. What is magnetic flux? Remember this, we have magnetic field, that is basically the number of, let's say, magnetic field lines. But when we say magnetic flux, basically, we can say something different. We can say how many magnetic field lines can pass through something. That is basically like a flux. So how about if I say, for example, something like a river, yeah? Of course, you can have a lot of water that is flowing through a certain area. And of course, the more the water is moving, you can say the more the flux, the more the flow of the water, yes? We can have something similar to that, not the same, but hopefully the analogy would help you understand a little bit. So we can say magnetic flux is basically the number of magnetic field lines. So imagine this, magnetic field lines basically crossing, or that cross a certain area, but remember it has to be at a right angle, let's say, to the plane of the area. That's this, and of course magnetic flux is measured in Weber. And of course Weber is basically equals to, later on we'll talk about each one of these, but just for now remember magnetic flux is measured in Weber, and Weber equals to basically Tesla times meter squared, that is 1, of course also equals to volt, basically times the second, and also could be used as, or this one, ammeter times, not ammeter, ampere times the ohm times second. These two basically for chapter 6, once we get to there, we'll talk about these in details. But for now, remember this. What was magnetic flux? Is basically the number of magnetic field lines that cross, let's say, the plane of an area, but remember it has to be at right angle or perpendicular. So do we have an equation for that? Yes. So what is the equation for that? Let me emphasize on this a little bit. So we can say magnetic flux is basically, here's the equation by the way, so let me rewrite it. And this is, you can say the symbol for magnetic flux, M stands for magnetic, and this is basically flux, equals to what? Equals to A, that is area, times B, that is magnetic field lines, basically cosine theta as well. When do we use cosine theta? I mean, by the way, if the magnetic field lines are perpendicular, then cosine theta would be 0. It's a little bit strange, but I'll tell you one thing. By the way, regarding the area, okay, do you know that area is also a vector quantity? Like, is that even possible? Yes. Area is a vector. That means it has both magnitude and direction. For example, if you have a ring, let's say, or circle, you can find the area. Yes? So area is basically equals to, let's say, pi r squared. Correct? Now that is the magnitude of the area, the value for the area. But what about the direction of the area? Did you know that area has also a direction? Yes. And how is it that? Remember this, if this is the plane of the area, the direction of the area is going to be perpendicular to this. What do we mean by perpendicular to this? Let's use blue here. Okay, so the direction of the area is always at right angle. Let's write M for that, yeah? So the direction of the area is always perpendicular or at right angle to the plane of the area. So if this is the plane of the area, so the direction of the area is always perpendicular to that. Remember, that is basically the direction of the area. So we can say this. Let me explain this a little bit more. And of course, this picture is also very good in terms of helping you understand this. So I'll get back in a second into this. So imagine this area. We said area has both direction and magnitude. Okay, so let's say this is the area, both magnitude. Let me write it a little bit far from this. And direction. So what is the difference between the two? For example, if this is, I have a circle, yes? So if I want to find the direction here, of course, the magnitude first, okay? Basically area, or the value for the area equals to pi r squared. But what about the direction? Remember this, that if this is the plane of the let's say, or the plane of the circle here, then of course it is going to be, I should have done it the other way, by the way. Let me erase this so that you can see the difference. I can draw it in two different ways, by the way. So let's draw this one. One time is like this, okay, and then the other time it is like this one here. Or perhaps let's make it a little bit this way so you can see the difference, okay? So if that is basically the circle, perpendicular, or the direction of the air is going to be perpendicular to this. So here is the direction of the air, which is normal to the plane, okay? If the circle is like this, it's going to be this way, it is normal to what? To the plane of this, you can say circle here. So these are basically the direction of this, okay? So now going back to the magnetic field, yes? So now this is basically the direction, normal. Normal what? Normal to the plane. Normal to the plane of the area. Okay, now since you know this, of course I'm going to erase this now because I'll use this one for a different purpose now. Right, so erasing this. Now let's talk about magnetic flux, or what is magnetic flux like in detail. So we can say magnetic flux is basically equals to A times B cosine theta. So what is magnetic flux? Basically, magnetic flux tells you the number of magnetic field lines that are crossing the plane of that area, let's say, or circle. So imagine this. These are basically magnetic field lines, okay? So the more the field lines crossing the plane of this area, basically plane of the circle, that means the more the flux. So you can say these red are basically B, yeah? So by the way, so now we have area, of course, that is obvious. So we can say area times magnetic field lines, and of course cosine theta. By the way, this cosine theta is basically the angle between what? Between the magnetic field line to the plane of the area. So if the plane of the area is like this, and of course the magnetic field line is like also like this, perpendicular to the plane of the area, what is the angle between B and the area? And of course the angle is 0, yes? Because you can see here, if that is the case, if magnetic field lines were like this, just remember, magnetic field lines were like this, the area's direction is like this, the angle between the two would be 90, yeah? But because these are both in the same direction, okay, in this case that means this is for B and this is for area, because they are in the same direction, so the angle between the two is 0. So moving on with this, we can say cosine 0, yeah? Okay, cosine theta, theta in this case is going to be 0 here. Let's use red again, cosine 0. And of course, you do know that cosine 0 equals to 1 in this case. So of course, we can say we can have maximum magnetic flux when cosine, let's say, or when the angle is 0. And in this case, it will be A times B, area times magnetic field strength. That is magnetic flux. What happens if these are not at, let's say, right angle to the plane of, let's say, this circle here? Okay, in this case, we can say, imagine this. Let's say here's the field again. Let's use blue. How about if I clean this a little? No, actually, I'll keep it here for a second. If this is, let's use blue again. Okay, so here's the plane of the area, and this is normal to the area. But what if magnetic field lines were like this, at an angle here? Okay, and this is, let's say, how about if I use different colors so you see the difference between the two? Black, okay. And here's the magnetic field lines, let's say. And of course, I'll just take one so that it doesn't become messy here. So if that is the case, of course, this magnetic field line can be resolved into two components, yeah? If that is one component here, that is X component, you can say, and of course, it resolved to another component, which is Y component here. Which one do we have to take? And of course, this one. Remember, we have to take the perpendicular component this, because this one does not cross the plane of this, so of course no magnetic flux, you can say. But this one here crosses or passes through this. So whenever you have an angle, make sure that you are taking the perpendicular component so that it becomes perpendicular to the plane of this circle or whatever, to the plane of that area, whatever the area is. So in this case, of course, if we are given at an angle, so we can say magnetic flux, it becomes what? It becomes A times B cosine theta. So remember this. This cosine theta, it is between what? It is between the magnetic field, okay? Or you can say the angle between the magnetic field and, of course, and the perpendicular component with what? Let's say with the area, you can say. That would be this angle right here. And of course, we have zero flux or magnetic flux if the angle is, or you can say the angle between the plane of the field and of course the magnetic flux is zero, just like, 90, just like this one here. Because in order to have magnetic flux, magnetic field lines must pass through the plane of that area. So what do I mean by this? Let me re-emphasize on this just one more time. So imagine this, if this is the plane of this, if magnetic field lines were like this, you can see that they don't cross through the plane of this area. So in this case, the magnetic flux here is going to be zero here. Okay, just remember this. So in order to have magnetic flux, then this magnetic field lines must be at right angle, or you can say normal to the plane of this area. That's one. If there was an angle, always take the perpendicular component. Okay, so these are basically the equations. Now let's talk about the unit for this a little bit. So this is magnetic flux, you can say, AB times this. If there is an angle, we can say A times B cosine theta. What about the unit? Okay, and of course we can say, let's use this. We can make the magnetic field strength as a subject here. So B equals to what? B equals to magnetic flux over what? Over the area. So remember, what was the unit for B? We said it is Tesla. Do you know that? What about the unit of magnetic flux? Magnetic flux is basically Weber, okay? And the unit for area, it is meters squared. So remember this. We can say Tesla, it is equal to Weber per meter squared. Or as a multiple choice, let's say I might tell you what is Weber over meter squared, and you should be able to know that it is equal to Tesla here. Okay, and of course this is more to that. This here, that is basically magnetic flux equal to B, that is magnetic field lines times the area. If there is an angle, always take the perpendicular component, so B times A times cosine theta. So this cosine theta is, once again, it is the perpendicular component of B, let's say, normal to the plane of the area. All right, now one more thing that we have, take a look. So we have magnetic field line, and we have magnetic flux as well, okay? And of course we have something is called the intensity of the magnetic field. So there is intensity as well. What is intensity? You already know the intensity, that means when something, like when we have too much of something, that means there is too much intensity for that, okay? So for example, when you have two lights, one of them gives more light, so the intensity, of course, it is going to be bigger, yeah, compared to a light that is dim, let's say, if measured at the same distance, let's say. Okay, so, but what about magnetic intensity or magnetic field intensity? We can have, let's say, two magnets. Let's say we can have two magnets of the same size, or the size could be different, by the way, north and south, let's say. This one, let's say, has just two magnetic field lines, yeah? But then the other one, you can see that it has a lot of magnetic field, let's say, lines. In this case, we can say the intensity of this magnet, or the intensity of the magnetic field of this magnet, it is bigger or larger than the intensity of the magnetic field of this one here. That is just for the sake of the comparison. Otherwise, we can have a small magnet that could have more intensity than this in terms of the magnetic field lines. So the intensity of a magnetic field is larger at the poles of a magnet, like we've said before. And of course, if we can say because the lines are closer to one another. So the closer the lines, that means the more the intensity. The more the intensity, that means the stronger the force as well. And this is one of the reasons why magnets can pull stronger at the poles here. Okay. Now let's talk about the last thing perhaps for this session, magnetic hysteresis. What is magnetic hysteresis? Now, this one is also something that is related to magnets. So let me give you an example of magnetic hysteresis. Or let's perhaps use this diagram to explain this. So let me get this. Okay. Magnetic hysteresis. is, remember this. Do you know that we can magnetize, let's say, iron? Let's say steel would be best if that is the case, or it could be an iron as well. But an iron would be like a let's say temporary magnet if it is a soft iron. Yeah. If it is a steel, it can retain it as magnetism, or it can stay magnetized for a long time. Let's say, or sometimes we call permanent magnet. Yes. If it is a sometimes we have, let's say, like steels can be basically turned into permanent magnets. But if it is a soft iron, then it is only temporary. And of course, they both have their let's say benefits as well. Okay, so let's talk about the first thing here that we have. Let's say we have a magnetic field, okay? Or basically, we have a piece of iron, or it could be, let's just say iron for now. And then, of course, we have a magnet here. Let's say this is north, and of course, just like this picture that you see here, and this is south. Or maybe you can switch the poles. Does it make any difference? In this regard, no. This is north, and this is south. Okay, so what happens when, of course, when I bring this magnet closer to this iron? So remember this. Now, when I bring this magnet close to this iron, of course, this iron will be exposed to these magnetic field lines. Do you know that? And if that is the case, then of course, the iron, or you can say the domain, okay, of these irons, basically the the domains of these irons would align themselves so that once they are under the magnetic field, they also becomes, the iron becomes a magnet as well. But how does it do that? It happens by using this curve in here. So this curve is basically tells you what? We have a magnetic force, basically. These are basically H, you can say. And of course, we have the flux density. Flux density, that would be, you know, like when this iron becomes a magnet, it would have its own magnetic field as well. Correct? You agree on this? Okay, so, but the direction is not, or the relation is not directly proportional to one another. So how does it happen? Remember this. As I increase or bring this magnet closer to this iron, let's say, or ferromagnetic material, then of course there is a magnetic force acts on this. So basically we can say, when I increase, let's say, the magnetic force, let's say, or you can say magnetizing force on this iron, of course, you would see that here, okay? This basically, this iron, of course, you can say, or the intensity of the magnetic field for this iron increases here. But you can see that it is not a direct proportional until it comes to this point here. This point is basically where you can say the maximum magnetic flux, or you can say flux density for this iron. So even if you increase the magnetic force, the magnetic flux density for this iron will not increase to this more than this. So basically this is the maximum capacity for this iron to become a magnet, let's say. That is the point there, yeah? So what happens, you can see it is a curve here. So this is the point where it saturates. It can no longer become, or this flux, you can say, it no longer increases anymore. So what happens when we remove the magnetizing force? If I remove the magnetizing force, then of course you would see that this iron bar would keep some of its magnetic flux density, you can say, or flux density generally, yes? So that is basically what it happens. So how can I demagnetize? So basically this iron becomes a magnet, let's say, or this ferromagnetic material. So how can I demagnetize it? Because it is magnetized now. If I want to demagnetize, then of course I need to apply a demagnetizing force onto this ferromagnetic, let's say. And if that is the case, of course, I'll get something like this. Yeah. If I keep the force increasing, let's say, then of course the magnet would, of course, or this piece of ferromagnetic would be magnetized, but of course in opposite direction here. So once again, that is basically what happens here. So what happens when I remove the force? Then of course I'll get, or this iron would retain some of its magnetism. Then if I want to demagnetize it, then of course I'll have to apply a force, but in the opposite direction here. So of course this is what I'll get, yeah? But then if I want to do this, then you can see here at this point, if I increase the force, then you can see that this magnetic, of course, or iron becomes magnetized one more time. So of course you can see that we get this shaped, you can say, curve in here. So this is basically, this process, you can say magnetic hysteresis. That is one thing. And this shape, or this loop here, you can say the hysteresis curve, the hysteresis loop as well. To make this one simple for you, let's go through these points in order for you to understand more. When a ferromagnetic material, a piece of soft iron, is exposed to a magnetic field, it becomes what? Magnetized. So the magnetic flux density increases non-linearly, as you can see here. Okay, so the magnetic flux density, you can say, increases non-linearly, as you can see here, with the increase of the applied field, or you can say the magnetic force field here. So when the applied magnetic force field is removed, this piece of iron still becomes, or remains as magnetized, let's say. That is the case. So the material retains some of its magnetism. This phenomenon is what is called what? What is called magnetism, or you can say magnetic hysteresis. So basically magnetic hysteresis is the process of magnetizing something. And then the phenomenon that is this. What about the curve? Well, the curve of the magnetic field versus the magnetic flux is called the hysteresis curve. Sometimes you can call it the loop as well, because we have a loop in here. So as you can see here, by the way, by increasing this magnetic field line here, that is basically this what happened, and you can see this magnetic field is basically for the iron. So we have the definition magnetic hysteresis. It is when the magnetization of a material lags behind the charges or the changes of the applied magnetic field, resulting in a loop-shaped graph, and that is basically what we have. I don't know, let's finish these two questions perhaps, and then we'll continue for next time, inshallah. It says, take a look at chapter reviews, that's 5.1. It says, when a bar magnet is broken in two pieces, how many poles will you get? There's always two. You can never ever have a pole. The last question here, which let me go through this one also very quick. It says, which of the compass needle orientation in the figure might correctly describe the magnetic field at this point here? Guys, whenever you're given something like this, always draw the magnetic field lines. Magnetic field lines is always from north to. Let me make the line thinner so that we can see or do this perhaps a bit better. So always draw magnetic field lines here. You can do this, okay, from north to south. Perhaps one line is enough. Could have drawn a little bit better here. Okay, and of course north to south in here. That's a potato shape or whatever. So which one of these is correct in this case? Which one of the or needle orientation of the figure might correctly describe the magnetic field that points or at that point here? Take a look. Is this, no? All right, here's the direction of the magnetic field from north to south. See, if the needle is aligned in the same way, that is correct. If not, it is incorrect. Is this one in the same direction? No. Okay, because you can see that it is moving away. So this is move or points the other direction? No. What about this one? No. What about this one here? So you can see that this one, it is pointing in the same direction, so this is correct. What about A? A is also pointing in the same direction, so this is also correct. What about F? F is pointing in the opposite direction. Here's the direction, so not this one. What about E? What about E here? You can see that E, or the magnetic field line at E, it should point this way, but you can see that it is pointing the other way, so which is incorrect. So the only correct options are A and B. Sorry for the drawing, it is a little bit mess, but you can see what it is. If it is in the same direction, it is correct. If not, if it is pointing in the same direction, it is correct. If not, it is incorrect. Now try to practice these Wrya questions, and next time, inshallah, perhaps next time we'll practice some of them before we move to the next lesson, which is going to be magnetism from electricity. Till then, keep practicing, and I'll see you next time. Assalamu alaikum wa rahmatullah.